the stall speed reduces. So you can go back and recap on why that is, what the effective power actually is. There's a bit of a introduction to what a spiral dive is and why that can actually happen. And this is something we actually demonstrate to them in the aeroplanes so that they're aware of the symptoms and how to recover, because what's the worst thing that could happen in a steep turn is they don't apply enough back pressure and they'll enter a spiral dive. On the aircraft management slide, you're introducing VA. I don't believe that's been talked about in previous briefings, so give some background information, and again, refer flight manual at the end of the briefing so that you can find those speeds in there. Give a little bit of background knowledge on how VA is affected, so why it's got two different speeds for two different wake ranges. Keep it simple. This isn't a lecture on steep turns or turning or load factor or aircraft limitations. You just want to keep it simple and practical. With the air exercise stuff, you could ask them how to enter and maintain an exit from a medium turn, because really it's very much the same. The only addition here is that we are adjusting the power setting. Otherwise it's the same process. So you could ask them that, you could ask them to verbalize it, you could ask them to draw it up, or you could just go click, click, click through the PowerPoint. And that's up to you. And then there's some more picture slides just to recap. There are a couple of videos. I don't think there's anything else I want to discuss with you. The whole 24 inches. Look, they don't get too carried away with the numbers. In the SOP it says to increase the power to 24 inches. But really, you increase the power as required to maintain the speed. You think about when you do steep turns in the poor visibility configuration. When do you ever increase the power to a set amount? You don't. You increase it as much as you need to maintain 80 knots, right? And why should it be any different in normal configuration? So yes, we have an SOP, but when you actually teach this in the air, you don't need to say increase power to 24 inches, because all that's going to do is encourage them to look inside at the manifold pressure. It's exactly what they shouldn't be doing. So a slight increase in the power to maintain the speed. And as you do your instrument scan, check to see if the speed is actually constant. That's probably about all I think I need to talk about. So about 30 minutes for this briefing. In the CAA Flight Instructor Guide, I'm pretty sure in this briefing they have a little bit of information about, what would it be? Steep gliding turns comes up in here, but it's only like a paragraph, because essentially it's the same considerations for that briefing as well. But that is where you'll find it. This thing wasn't working, was it?
It was working to the point that, towards the computer.
Okay, right. Okay, so for an intro here, state how long it's going to take, approximately 30 minutes. And we've learned previously about medium turns, the forces acting on the aeroplane. We've learned about rate 1 turns, and we learned that the steeper the angular bank, the greater the rate of turn, and the smaller the radius. That is stuff that was introduced to them in the medium turns briefing. Today we're looking at a situation where we either want or we need a higher rate of turn and a smaller radius of turn. So steep turns. And really a steep turn is a maneuver. We practice at 45 degrees, but it's a turn where the angular bank is greater than 30 degrees. No more than and 60 degrees in a DA40. Here are our objectives. You'll notice they look very similar to the medium-term objectives, just using 45 degrees angle of bank for this lesson as opposed to 30 degrees or less. We're still looking at maintaining constant altitude in today's lesson and keeping the aeroplane in balance. What is slightly new today though is we want to become familiar with the sensations of higher angles of bank and high rates of turn. What is different from the medium turn? That's what we want to do today. Throughout your training, we'll have a look at steep turns through 360 degrees, 180 degrees, and with a variety of different scenarios so you can really see how these turns are applied in a real world context. This next slide should just be revision, so you could ask them before you bring everything up, why would you want to turn? Write it up on the whiteboard or just click through it if you want to. Briefly touch on each point if you think you need to. So I don't need to actually explain these to you. There may be a few new things here like coordination skills. It's a good exercise for practicing coordination because it's an avoidance maneuver. If you think about it, let's say we're out in the training area and we see cloud ahead of us, so we think, right, we'll start with a medium turn, and then we realize, no, the rate of turn's not sufficient enough, we're still going to fly into that cloud. We'd want to roll into a steeper turn. We're going to require varying inputs on the controls. The airspeed, the effectiveness of the controls changes as well. So mention that, and that'll flow into the max rate briefing quite nicely as well. This is all the same considerations in that briefing. It is a flight test maneuver, but anytime we want a higher angle of bank, so a higher rate of turn or a reduced radius of turn, maybe because we're operating in a confined space, this is where a steep turn is going to be beneficial. So really emphasize that. Overall, it's an avoidance maneuver. Here's an overview of what we're going to be talking about today. So it follows the same kind of format as the medium turns briefing. You really don't need to go into detail here. Here's a bit of a recap on a medium turn. So hopefully you still remember how to judge attitude. We're visual pilots, so we look outside to judge this. So positioning the nose in relation to the horizon, and we can judge the angle of bank by the angle between the horizon and the cowling or some other data. So this is what a 30-degree turn, in this case to the right, looks like. With a steep turn, we're going to look outside to judge that as well. Here's a steep turn to the right. So still the level attitude, the nose is still on the horizon, but now the cowling and the horizon's at a 45-degree angle. So this is what the picture should look like. Okay, same thing to the other side there, okay? Emphasize level attitude, how to judge that, and emphasize judging the angle of bank. So no matter how steep the turn gets, we should always have the nose on the horizon. That should not change. So far we've talked about rate 1 turns and medium turns. The rate 1 turn has a variable angle of bank depending on the speed. The medium turn, as you learned, what angle of bank is that? Ask that question, 30 degrees. For the steep turn we're going to look at today, we practice at 45 degrees angle of bank. And there is an aircraft limitation, no greater than 60 degrees angle of bank in the normal category for a DA40. Again, that's something you could show them in the flight manual at the end, or get them to find in the flight manual, because by now there are more advanced students, so they should have a basic understanding of what's actually in the flight manual itself. So it's up to us to decide which type of turn is appropriate. So it depends on the situation that we find ourselves in. The next slide is a recap on forces. One click brings up this whole thing, so you don't need to go through click by click for the medium turns part. What you're going to do is just compare the forces in a medium turn with the forces in a steep turn. So, I don't know, tell some sort of story here. We're out in the training area and we see cloud ahead of us. We need to avoid the cloud, so we've decided, right, we'll do a medium turn to avoid it. But partway through that turn, we've realised we're still going to fly into the cloud. So we elect to steepen the turn up to 45 degrees. And let's have a look at how the forces change in that turn. So you can recap on the vertical component lift. You could ask questions like, why did we have to increase lift? What were the effects of increasing the lift? So maintain altitude, and we get a bigger horizontal component of lift. Ask questions, there's no need to teach that stuff again. Now what about when we are in the steep turn? No change to the weights there, but in order to get to that steeper angle of bank, we've had to roll in more. So now the lift is even more tilted in the direction that we are rolling. There's our vertical component of lift. Hey, so you can see that it's less than the weight. So what will be happening here? So what do you need to do? See how you can just ask questions? It's really just revision based. Hopefully they remember, yeah, we need to increase the angle of attack. Another effect of increasing the lift is that the horizontal component of lift increases. Now this is important here today because we are interested in an increased rate of turn and a reduced radius. We want to use less space to turn around, and it's this component of lift that controls that. So it is, the steeper the angle of bank goes, the more lift we need, but the greater that horizontal component of lift can be. The higher the rate of turn, the smaller the radius. Now, do you remember any of the effects of increasing the angle of attack? Pose that one as a question if you like, because in previous briefings, you've talked about increasing angle of attack increases drag. And that will bring it, that's really where the briefing goes at the end here. So increased drag, and what effect do you think that might have on your airspeed? Yeah, so questions, okay? You shouldn't need to just do all the talking on this slide. Another question you could ask, so how might we prevent that loss of airspeed? In the medium turns, you know, we didn't care about it. Here we are going to look at maintaining airspeed. So how do you think you'll do that? It may seem obvious, but do ask that question. We've talked a little bit about load factor before, so you know, ask the questions about what all of that is. Be prepared to give some more information. So it's a measure of the extra lift compared to the weight. You can think of it like, have they ever been on a roller coaster and they felt like they're being pushed down into their seat? That is loading, also known as G, or apparent weight. The next click brings up this little grid. So here in straight and level flight, you can see lift is equal to weight, so the load factor is 1. Show you the length of the vectors there. Now what about at a 45-degree angle of bank turn? The weight hasn't changed there, but as we've just seen, we need to increase the lift so that we can fly level. And a reaction to that is that the loading is going to increase because now lift is greater than weight. Another click shows you that. And in a steep turn, 45 degrees angle of bank, the load factor is 1.4. That means 40% more lift is required to keep the aeroplane in level flight. The steeper the angle of bank goes, the greater that load factor will be. Little statements like that towards the end will be useful because soon they will be doing max rate turns, and that really is just an extension of this briefing. Hey, do you remember the effect of load factor on the stall speed? That leads you quite nicely into the next slide, which is this grid. So you can highlight there that they may not be aware that there's a formula for calculating the new stall speed. You don't really have to go through any examples here, but that might be a useful formula for them to actually remember, and certainly is for you guys. You should all memorize this and be able to manipulate it to get an answer. So let's have a look at how that stall speed changes with the load factor, and also what happens to drag as we roll into steeper and steeper turns. So firstly, let's imagine we're flying along in straight level flight out in the southern training area. You could ask them, what was the load factor? Yep, that's 1. What about the stall speed? Well, there's no change in the stall speed. So what was the basic stall speed? Oh, yep, 53 knots. And drag. Drag doesn't increase, so we'll just say there's a set amount of drag in straight level flight. Now what about, there's that cloud there again, so we've decided to roll into a steep turn. So load factor was 1.4. Stall speed. Now this is where, get them to actually calculate the stall speed on their phone or calculator or whatever. So there's a percentage increase in the stall speed, approximately 20%. If you're being really accurate, it's more like 18% increase. So what will that be? 63 knots is our new stall speed for a steep turn at 45 degrees angular bank whilst maintaining altitude. And there's a doubling of the induced drag. That angle of attack has had to increase so much that there's now far more drag. So what do you think that'd do to the airspeed? Oh, it'd reduce. Our stall speed is rising and our airspeed reduces. Introduce that here, because that will lead you into the next slide as well, which is going to be the power sandwich. What about a 60-degree angle bank turn? This is something you're going to learn much more about later on in your training. So we're just talking about it here for comparison. The load factor is 2, so that means we need twice the amount of lift that was required for straight and level flight. It's a pretty steep turn. You could get them to calculate the percentage increase in the stall speed as well as the increase. So 40% rise in the stall speed becomes 75 knots. Now, the drag increases by a factor of 4. So once again, we've got airspeed reducing, we've got stall speed rising. What you could talk about here as well is, imagine we're on final and we see that there's an aeroplane in front of us. So we decide to take evasive action. We decide to roll in to a 60-degree angle bank turn. What is our approach speed? It's 75 knots. And we've just rolled to a 60-degree angle bank turn. Our stall speed is 75 knots. We will stall in that turn as we try to avoid it. So highlight, the awareness is required. And again, like I said, at some point in this briefing, probably at the end, introduce them to all of this stuff in the flight manual as well. So as I said, talking about the fact that the airspeed's reducing, the stall speed rising is going to lead you quite nicely into this. So in between the airspeed and the stall speed, we have what is known as the power sandwich. So we've just discussed that as that drag increases, the airspeed's going to reduce. And we've discussed that as the angle of bank increases, the load factor increases, and the stall speed's going to increase. Have a look at what happens to that gap in between the two. What happens to the power sandwich? It reduces. And if the two meet, we will stall. This is undesirable, as you've learned in previous lessons. So what can we do about this? Well, there's not much we can do to control the stall speed rise, but we can control the airspeed. How do you think we do that? And another click there brings up power. So increasing power there helps us to avoid a loss of airspeed, and it also affects the stall speed. Do you remember what power did to the stall speed? Be prepared to give additional detail there if you needed to, because remember, approach stalls were done some time ago, so maybe they don't recall the effect of power on the stall speed. If you did need to talk about it, remember vertical component of thrust and also the delayed separation. For this slide, what I normally lead into it with is, remember back to medium turns. Remember how on some of those turns you forgot to, or you didn't increase the back pressure enough? What happened? Oh, we entered a descent. It's a fairly shallow spiral descent, and the same thing can happen in a steep turn. Only now we've got a steeper angle of bank, and we could enter what is known as a spiral dive. So it's important that you're aware of why this might happen, what the symptoms are, as well as the correct recovery. It's a really wordy sentence or two that comes up there, but I just get them to read it. It's a bit technical as well. Essentially though, if you don't increase the back pressure enough, the aeroplane will descend, and it's partly due to spiral instability. Will enter a spiral descent. What are the symptoms? You could ask them about what they think the symptoms will be. Otherwise, highlighting there that the rate of descent will be high, potentially increasing. The nose attitude will be low. The angular bank could be increasing, steep or steepening. Sometimes there's an increase in the G as well. This is that angular bank gets steeper and steeper. They may actually be able to detect the increase in G. One that I don't think comes up on here but is really relevant is the noise changes. In a DA40 you hear the increase in air noise from the increased speed. In a aircraft like Foxy, you will see the RPM rise, but more importantly you will hear the RPM rise. It's a real telltale that, hey, you're not maintaining altitude. So what do we do for the recovery? We've detected that we're in a spiral dive here. The recovery is going to be to close the throttle to stop the airspeed increasing anymore, smoothly roll the wings level whilst maintaining balance. Then we can pitch the nose up to the horizon and add power once the airspeed has resumed to a normal speed. And as required, climb back up to the reference altitude. As we've discussed in previous briefings, we are visual pilots. We spend most of our time, 80% or more, looking outside at the picture and looking out for hazards. We do need to have a quick scan of the instruments to confirm performance though. We don't want to chase the instruments. So today you will learn what these attitudes and angles of bank look like, how to judge what a steep turn looks like, and then we will scan the instruments to confirm the performance. So what instruments do you think are relevant? Link it back to the objectives. What do we want to do? We wanted 45 degrees angle bank, so the AI. We want to be in balance, so the slip skid bar. We want to maintain altitude, so our altimeter. I really don't need to teach you anything about the lookout there, but it's probably a common fault with students is not doing a thorough enough lookout before the turn and during the turn. So really highlight there, take the time to ensure that the area is clear, and throughout the turn, let's keep that activity cycle going so that we are looking outside for any hazards during the turn. Think about it, this is an avoidance maneuver. Who cares what the instruments are saying inside? If you're about to fly into cloud, wouldn't you be looking outside to make sure that you weren't going to do that? Real world flying, of course, you're not going to be looking inside, disorientation. There's a slight increased likelihood of you encountering disorientation in these turns because of the steeper angular bank and the higher rate of turn. How can we counteract that? Like medium turns, pick a prominent reference point that you can easily identify for your rollout. And keep the scan, the activity cycle going to look out attitude instruments. Combination of those things will help to avoid the risk of disorientation. Recap on I'm Safe if you want to. They should be experts on that stuff by now though. Probably the relevant one is motion sickness. Again though, I find it's pretty rare for students to get motion sick in steep turns, but perhaps the combination of a bumpy day with repetitive steep turns, that could induce motion sickness, so be alert for that and reassure your students. As with all the flying we've been doing so far, we want smooth inputs. You'll find smooth inputs on the controls much easier to set and maintain attitudes and angles of bank. We don't want to be aggressive or abrupt. It'll actually be harder to fly the steep turn accurately. And not as smooth, not as comfortable. Something we haven't talked about before is a speed called VA, the design maneuvering speed. This is the maximum speed at which you can make full and abrupt control movements without risk of overstressing or over-damaging the aircraft. Above those speeds, if you use full and abrupt control movements, you can overstress the airframe. Things like the spars, the main structural parts of the wings, could be damaged or even snap. Think about a ruler. If you bend that ruler too far, it will snap. The same thing can happen to an aeroplane if we apply too much force. So these speeds for a DA40 can be found in the flight manual, and they're also placarded in the aircraft. You need to memorise them. There's two speeds for two different weight ranges. Below 1,036 kgs, it's 111 knots, and below that it is 94 knots. You need to memorise those speeds. And at the end of this briefing, we'll spend a bit of time talking about the flight manual and where to find them. So why does the VA speed change with a change in weight? They're not going to know that. You need to know that. What is the answer to that question? Why does, just keep it simple, why does the VA speed change with weight?
Loading greater?
Sorry?
Loading greater?
Loading greater. Can you explain that?
Yeah,
What do you mean by that?
Weight's more, you get more lift, loading more.
Isn't the loading the same? If I do a steep turn in a 747, 300,000
Yeah.
kgs, the load factor at least is the same, isn't it?
Isn't it just because the weight's going to change the stall speed?
That's part of it,
it's the inertia.
inertia. Yeah, so you can talk about two things here. What I would talk about is inertia. So a heavier aeroplane has more inertia. So if you were to use full and abrupt movement in a heavier aeroplane, it will take longer to respond. A lighter aeroplane has less inertia. The loading does build up faster in a lighter aeroplane, so you're more likely to overstress the aircraft. Is that what you were meaning when you said like change in loading? Yeah.
I said that to Craig in my test.
So it's not about the load factor, it's
That's what
about
you told
like
me
the
that's
loading
what I
itself, how quickly it builds up.
Inertia.
The stall speed one, if you don't have to mention that, but when your airplane is heavier, for a given airspeed, you would have a higher angle of attack, wouldn't you, to produce the necessary lift. So what does that mean? That means you're closer to the stall angle, and that means, let's take it to an extreme. If we overloaded the DA40 so that we're actually cruising along in straight level flight like that with full throttle, let's just really exaggerate it. We're almost at the critical angle. If you rip back on the stick, you're going to stall almost immediately before there's any chance of the loading building up to overstress the airframe. So the heavier you are, the closer you get to the stall angle, and the less likely it is that you'll actually overstress the airframe. So that's an alternative explanation. But keep it simple here. There's no need to go overboard. It's a relatively complex thing to understand. So we talked about how the airspeed reduces, the stall speed rises, and we don't want the power sandwich to reduce. So by increasing power, we keep a healthy margin between the speed and the stall speed. For a steep turn, we have an SOP that we use 24 inches of manifold pressure. And this is only really for the clean configuration. Later on, when we look at steep turns in the poor visibility configuration, it's power as required. I want you to think of these steep turns today still as power as required, because if you scan the airspeed indicator and you find that airspeed is lower than normal, I want you to increase the power more. We don't want to have our eyes glued inside at the manifold pressure. The steeper the turn goes, the more power you will need to maintain your speed. As I said with the ear exercise, ask them some questions if you want. Do you remember how to roll in, enter a medium term? What about maintain it? What about exit? Look, if they can actually give you a well-polished answer to that, your job is done. All you need to do now is just check they didn't miss anything. So I don't need to teach this to you, okay, but like the medium turn, emphasize that they have a reference point, reference altitude, thorough lookout. Then there's the roll in, it's coordinated. You'll find that you'll need to ease back more as you roll in because we need a higher angle of attack, but it's still the same level attitude. And as you roll in, keep your eyes straight ahead, because straight ahead is where it is easiest for you to judge that the attitude is remaining constant. So where students struggle is they're looking in the direction they're turning as they roll in. They've just done a lookout. They know there's no object there. So if they look straight ahead as they roll in, they'll see that the attitude is staying the same. We'll establish the aeroplane at 45 degrees angle bank and prevent overbanking, just like the medium turn, increasing the power through 30 degrees angle bank to maintain speed. And we'll note the angle of bank and the attitude today and hold that all the way around the turn. Maintain it. Okay, same thing there. I don't need to teach that to you guys. Emphasize that it should be more of a rapid scan this time. Things are happening quicker. So a more rapid and continuous scan of lookout attitude instruments. You'll have heard me say this multiple times by now, but any problems that arise, they're going to be because the lookout attitude instrument cycle has fallen down. Either they've fixated or they're going too slow. Because it's a slightly steeper angle of bank and the rate of turn is higher, we'll need to anticipate the rollout slightly earlier than for a medium turn. We'll roll out in balance, relaxing the back pressure to maintain the level attitude, and then we'll reduce the power back to the normal straight level setting. Before we do that, confirm the airspeed is normal. Today I will demonstrate to you the spiral dive and the symptoms as well as the recovery. So if you wanted to ask some questions about that here, you could do, hey, what were the symptoms? Hey, what was the recovery? So just to recap on what the pictures may look like, we're going to start with some medium turns today, just so we can really re-familiarise with what the level attitude looks like in a turn. Here it is for the medium turn to the right. Here's the seat turn to the right. Note the nose is still in the same place on the horizon, but now the cowling's at a 45-degree angle of bank. Steep turn to the left, still the level attitude. Now the cowling is at a 45-degree angle of bank. And then there's a bit of an animation. I think that's all it does. Really, the only point of this bit though is to highlight that the attitude stays the same. So noting there that the nose is not pitching up or down relative to the horizon. That's all that slide is for. There are a couple of videos. I'll show you one of them just as an example of what you can do. So, have a bit of a discussion, right? We're picking a prominent reference point, reference altitude, having a good lookout. Now we're going to roll in and coordination, increase the power through 30 degrees, establish 45 degrees angle bank, prevent overbanking. Now we're established. Lookout attitude instruments, a rapid cycle, rapid scan, making adjustments as required throughout the turn, keeping that cycle going all the way around until we are ready to start rolling out. And then discuss the rollout. So coming up to our reference point again, we anticipate slightly earlier rollout than for a medium turn because of the higher rate of turn. Rolling out in balance, relaxing the back pressure, confirming the airspeed is normal, then reducing the power back to normal cruise settings. And we've arrived back at our reference point, still at the same reference altitude. And then you can show the one to the other direction as well, highlighting their judgment of angle of bank and level attitude. So that's it.